So we're going to go through Rings polymers analysis today from June 2012. So the first question we kick off with was about alkenes and benzene, both reacting with bromine. So this one comes up a lot, and we know it's all to do with electron density. In an alkene, you have two pi electrons which are localized over one carbon-carbon double bond. In benzene, however, you have six delocalized electrons over six carbon-carbon bonds. So therefore we can say that the electron density in benzene is less than an alkene, and therefore any electrophiles will be less attracted or equally less polarized by benzene. There you go. So that should really get you the full marks. Okay, so now we get on to some reactions. So we've got reaction 1 where a student's mixing phenolethene with excess bromine at room temperature, and we get an organic product. Let's draw that product. Well, they've told me what phenolethene is, so it is a benzene ring with ethene. So let's draw him out, like so. So you're coming to bromine there, so obviously the bromine is going to just pop across that double bond as expected. Predicting the number of peaks, well, let's have a look in the carbon NMR. 1, 2, 3, 4, 5, 6. I'd expect to see 6 peaks in the carbon NMR. In reaction 2, I now add a halogen carrier to the mixture obtained from reaction 1 and obtain a mixture of isomers. They now have 3 bromines on it. So I've got a halogen carrier. That, of course, is a key little hint to us that obviously we popped a bromine onto my benzene ring. So this is what I had from my last reaction. So I can put a bromine there for one isomer, and I could also put a bromine there for my other isomer, like so. State the type of mechanism take place. In reaction 1, you remember it was bromine added to an alkene, so that was electrophilic addition. This one, of course, we know at the top there is going to be electrophilic substitution, because I replaced the hydrogen on my benzene ring with a bromine. Rightio, on to some polymers now. I've got a nice skeletal formula of a polyester. One reason that the polyester is biodegradable is it can be hydrolyzed. Okay, another way. Well, we know another one that we know is it actually is photodegradable, so it degrades by the action of UV light on these polymers as well. When this polyester is hydrolyzed with aqueous acid, compound B is formed. Notice it's just telling me a compound B is formed. So this polymer is obviously made up from just one monomer. Let's have a look at this. Well, that to me looks like the repeat unit. Hopefully you agree. So let's just draw that repeat unit out, like so. Polyester, I'm going to start off with a carboxylic acid, like so, and an alcohol on the other end, like that. Right, on to our next polymer now, nylon, which we all know and love, which we've made it. We've got reacting butane 1,4-diamine with hexandioic acid. They give me the formula. I can synthesize the diamine from 1,4-dichlorobutane. What do I need? Well, I'm replacing a chlorine with an NH2 group, so we know that that, of course, is ammonia in ethanol, so excess ammonia in ethanol. It can act as a base, the diamine. How can it act as a base and write the formula? Well, always remember that the nitrogen atom has a lone pair of electrons that are donated to H+, therefore it is a proton acceptor. Formula of the salt, okay, so it's told me it's reacting with dilute hydrochloric acid. So, first of all, I'm going to put plus charge on each of these. Look. CH2 4 NH3 plus. So plus charge on both those nitrogens, because it's in hydrochloric acid, the counter anion is Cl- on both sides as well. Okay, so I'm going to now draw the repeat unit of nylon. I've put the two monomers up here because it was on the other page just to remind us. So when we draw, it's going to be a polyamide. So starting off with that nitrogen there, I then got my CH2 I then go to that nitrogen. He's going to go to that carbon there, CH2 times C double bond O, and make sure my next atom would be the N from that one there. So that there's my repeat unit, and that, of course, is my amide bond there. Okay, I've now got a protein here, and I'm going to now functionalise this, and it wants the structure of the zeta ions formed. So if I have a look here, that's my amide bond there, so that's where I'm going to go. Now, if I just draw these out, first of all, and then we will complete the rest. So you just break it at that peptide link, copy it out as before, but now this is going to become OH minus, that's NH3 plus, that's OH minus, and this is NH3 plus. Common error, some people put another H here, H plus here. Remember this time you've just got 1 plus, 1 minus, and that's all you need to consider. Why are they different? Why do they have different isoelectric points? It's because one of them had 2 NH2 groups, which is obviously going to affect the pH at which they become the zeta ion. So you need to look at the functional groups that you have. Okay, so we're now on to some fats and oils. Incomplete structures shown below. Add the double bond to show where it is. So it's octadecade 12 eno8. Remember that's number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my double bond goes there. State how the trans isomer, this is the trans isomer there, is different from the cis isomer. Obviously from the cis isomer, if I just draw that bit out again, that bit, the hydrogens would be on the same side there. So that is the trans, that one would be the cis if you wanted to draw them out. Make sure I've got the right number. But that clearly shows how the cis isomer is different. And in words, as it says on the old mark scheme, the cis isomer has the branches on the same side, or it has hydrogens on the same side of the carbon-carbon double bond. One possible health risk for high diet, which we have a lot of trans oil, is it does put you at risk of heart disease. It's not very good for you. Okay, nice one. You just got to count up your carbons here. How many carbons are there going to be? There are actually 27 in there. I won't go through the tedious nature of counting. Next one, how many chiral centres? I've marked them on for you. There are in fact 8 chiral centres. Remember, chiral centre, you need 4 different groups around that carbon, and each one of these you can see has got 4 different groups. This one may confuse you a little bit because you've got like carbon, carbon, carbon. But if you can see, if I'm taking a different route each time. If I was sat on that carbon, I'd have a different view depending on the direction I looked. Bit of information, it's a steroid. Let's have a look at it. What are the functional groups in this steroid? Well, you can hopefully see this boy here is an ester, and that guy there is, of course, an alcohol. One advantage of developing a synthetic route to this steroid, starting from a natural steroid, is, of course, if steroids come from a natural source, then it already only contains one type of optical isomer. We don't need to worry. If we're making it from scratch in the lab, then we get a 50-50 mixture. So we only get one of the optical isomers present, which is good. It ensures the correct chirality. Okay. Right, so compound C is an intermediate. 2-step synthesis of this from compound C for each step, state of reagent condition. Okay, that hasn't changed. It's this boy that we need to go. If you look at the molecule, if you look at the steroid, that has turned itself into an ester group. To make an ester, I need a carboxylic acid and I need an alcohol. That is not an alcohol. So the first thing I need to do is go from aldehyde to alcohol. And for that, as you know, I use sodium borohydride in water and I warm it up. The next one, once that's turned into an alcohol, I then go from carboxylic acid and alcohol to make an ester. I need concentrated sulfuric acid for that.